Welcome to the lecture series on process integration. This is module 4, lecture number 10. The topic of the today's lecture is cost targeting for optimal delta T minimum. This process of cost targeting to find out optimum delta T minimum is also called super targeting. We have seen that while solving a process of heat integration, where a hen has to be designed for a given duty, we have assumed some delta T minimum value and then we have proceeded for the design. This assumption of delta T minimum value was somewhat ad hoc in nature. Though there are guidelines to find out the delta T minimum values for a given process or for some streams like liquid streams, gas streams or the steam or the cooling water, they are not very accurate. Now, once we have ad hocly selected delta T minimum value, we have to prove that this delta T minimum value is correct to some extent, or we have to find out another value of delta T minimum which is best suited for that situation. Now, this lecture tells you what is the best suited value which we call optimal delta T minimum value for a given network. And to find out optimum delta T minimum values, we will use the process of cost targeting to arrive at a optimum delta T minimum value. This process is called super targeting. It is a fact that the lower value of delta T minimum usually reduces the utility cost by increasing the process to process heat transfer. This is a well known fact, and that we have seen this in the energy targeting. However, at the same time it increases the area requirement for hen due to the low driving force. This increase in the fixed cost of the heat exchanger network. Obviously, there is a trade off between this. That means, when we are decreasing the delta T minimum, we are decreasing the utility cost, but at the same time we are also increasing the fixed cost of the hen, and hence there are two opposite forces which are working when we change the value of delta T minimum, and thus it calls for optimization. This can be known very easily from the equation that U is equal to U, Q is equal to U A delta T ln, or A is equal to Q divided by U delta T ln. If the log mean temperature difference will decrease, the area will increase. For any heat recovery problem, the choice of delta T minimum affects the shape of the process source and sink profiles, and thus affects the heat exchanger network topology. Due to this, the fixed cost component as well as the operating cost component of the hen varies with the selection of delta T minimum. It clearly tells that the delta T minimum affects the operating cost as well the fixed cost. Since fixed cost and operating cost, which is in this case utility cost, because we are not taking pumping cost into this, are expressed in terms of different time scales. It is necessary to find out a basis for joining these two to find out the optimum value of delta T minimum. This clearly tells that when we are calculating fixed cost, the fixed cost is for the service period of the heat exchanger, while operating costs are expressed in terms of in yearly basis, and hence the time scales are different, and that is why to add them together we have to change the fixed cost to annualize fixed cost, and then only we can add to the utility cost or the operating cost. Now, this is required to find out the optimum value of delta T minimum. That means, we will convert the cost data to a TAC cost data, that is total annual cost data, and then we will plot this with delta T minimum to find out the optimum delta T minimum. The amount of hot and cold utility reduces, and thus its cost. When we are decreasing the delta T minimum. So, we are studying now the effect of delta T minimum reduction. What will happen if I decrease delta T minimum? The first thing what we see is that the amount of hot and cold utility reduces, and thus its cost also reduces. That means, it will reduce the operating cost of the heat exchanger network. The amount of process to process heat exchange increases. When I decrease delta T minimum, this happens, that process to process heat exchange increases, and thus the required area of the heat exchangers. As the process to process heat exchange increases, to transfer this amount of heat, we have to increase the area of the heat exchangers. This increases the fixed cost, that is capital cost of the hen. The third point is the overall temperature driving force delta T of the hen decreases when we decrease the delta T minimum, and thus the area of the heat exchangers present in hen increases, increasing the fixed cost of the heat exchangers. This is a very well known fact. If we decrease the driving force, area requirement to pass a constant amount of heat will increase. Loads of heaters and coolers decrease. When I decrease delta T minimum, my amount of hot utility and cold utility decreases, and hence the loads on heaters and coolers decrease. Thereby, its fixed cost also decreases. However, the increase in the cost of heat exchangers transferring process to process invariably outweighs the reduction in the heater and cooler cost. The main trade-off is between the energy cost reduction and the fixed cost increase. So, when we decrease the delta T minimum, our energy cost reduces, but the fixed cost increases. So, there is a trade-off between these two factors. The fixed cost is expressed for the total life period of the heat exchanger, this we all know. The yearly fixed cost is expressed as depreciation cost per year and is charged per year for the complete life period of the equipment. The utility cost, that is operating costs, are charged on yearly basis. Both the cost can be added if the time scale selected is 1 year. So, the total cost thus obtained is called total annual cost TAC. Now, for every delta T minimum selected, one can estimate the value of the TAC. Now, once I select a delta T minimum, I can do the area targeting, I can do the energy targeting. From area targeting, I can find out the fixed cost and then convert the fixed cost to annualized fixed cost, and from the energy targeting, I can find out the hot utility and cold utility demand, convert them into the operating cost, add them together to find out the total annual cost. So, I can say that the TAC is a function of delta T minimum and topology of the hen. Why I am talking about topology? Because for a delta T minimum, for a given delta T minimum, we can design many heat exchanger networks which can perform the job, but the cost of those heat exchangers networks will not be same, but they will satisfy the requirement, and these heat exchangers will form different topologies of Hen. So, for a given delta T minimum there can be many Hen designs, and thus we can say that the TAC, that is total annual cost of the heat exchanger network, is a function of delta T minimum as well as the topology of Hen. Now, what are the effects of delta T minimum on TAC? For a given problem, if for a large number of delta T minimum values, TAC values are plotted, one can get a value of delta T minimum which is called optimum delta T minimum, at which the TAC is minimum. The Hen should be designed for optimum minimum value. So, if I am able to find out the delta T minimum optimum value, which means that if I operate my heat exchanger network at this optimum delta T minimum value, then TAC of that heat exchanger network will be minimum. Now, this is our aim, because we want to pass a certain amount of heat using a heat exchanger network at a minimum cost. If I am able to save cost, then it will be reflected in terms of my profit. So, the aim is to run a heat exchanger network which will require minimum cost. This process of determining optimum delta T minimum based on cost targeting is called super targeting. Tiso and Leonoff in 1986 was first to develop super targeting method. Now, this can be seen by a plot here. This is plotted between TAC and delta T minimum, and the TAC of different heat exchanger networks, because when I am changing delta T minimum, the heat exchanger network is also changing. That means, I will have different heat exchanger networks for a given delta T minimum, and if I plot the TAC of those heat exchanger networks, then I find a curve which resembles to this, and this is the point where my TAC is minimum. So, this point of delta T minimum is called optimum delta T minimum. Now, let us take an example to demonstrate this. Let us consider the following example consisting of two hot streams H 1 and H 2 and two cold streams C 1 and C 2 as shown in the table below. Delta T minimum is taken as 10 degree centigrade and 20 degree centigrade. So, for 10 degree centigrade, I will first do the solve the problem, and then for 20 degree centigrade I will solve the problem, and we will see that what is the difference between a delta T minimum solution at 10 degree centigrade and vis-a-vis 20 degree centigrade. So, this is the stream data which is available for us, the H 1, H 2, C 1, C 2, C u, that is cold utility, and H u the hot utility. Their supply temperature and target temperatures are given, their Cp values are given, and their H values are given. The Cp values of cold utility and the Cp values of the hot utilities are not given to us, because we have to find out these values by energy targeting. Now, if I plot the grand composite curve for this problem, the grand composite curve looks like this. Now, here this is the pinch point, because this is shifted temperature. So, there is a single pinch point here. The hot utility requirement for this problem is 1550 kilowatt, and the cold utility requirement which is given by from this point to this point is 2550 kilowatt. Now, if I plot it for delta T minimum equal to 20 degree, I clearly see that the grand composite curve is changing. Here the hot utility requirement is 2100 kilowatt and the cold utility requirement is 3100 kilowatt. I can show you the earlier one for a comparison. This is for delta T minimum 10 degree centigrade and this is for the delta T minimum 20 degree centigrade. Now, here we see if we compare the delta T minimum values and the corresponding effect on the hot utility demand and the cold utility demand, we clearly see that when delta T minimum is 10 degree centigrade, the hot utility demand is 1550, but when it is 20 degree centigrade, this is 2100 kilowatt. So, the hot utility requirement has increased significantly when I am increasing the delta T minimum. Similarly, the for cold utility requirement was 2550 kilowatt for delta T minimum equal to 10 degree centigrade and it was 3100 for delta T minimum equal to 20 degree centigrade. So, it has also increased significantly. From the above table, one can see that the higher the value of delta T minimum, higher are the hot and cold utility requirements, and therefore, it appears obvious that one should have a low delta T minimum as possible to obtain maximum energy recovery or minimum utility cost. So, if we want minimum utility cost, I have to keep the delta T minimum as low as possible. However, there is a other side of it also. The surface area required for a heat exchanger is given by A is equal to Q divided by U delta T Lm, where A is the heat transfer area in meter square, U overall heat transfer coefficient and delta T Lm log mean temperature difference. This is a very well known equation or expression. The log mean temperature difference can be computed using equation 2, which is also a well known equation. So, I do not have to discuss it more. The lower delta T values in large and more costly heat exchangers, as it tends to increase the area of the heat exchanger. So, when I decrease delta T minimum, the fixed cost of the heat exchanger network increases. So, there are two opposing effects. Therefore, it is important to choose the right value of the delta T minimum for network design. This can be done by cost targeting for optimum value of delta T minimum. Now, a industry is run for profit making. So, every decision is based on profit. So, here also the profit will be the last say, and that is why we will select a delta T minimum or we will compute a delta T minimum which will maximize our profit or minimize our operating cost. Now, when we do this process is called super targeting. Now, if we see for the given problem, what happens when the delta T minimum is increased? We see that when the delta T minimum is low, the area is high, and when delta T minimum increases, the area decreases, and then slowly it goes to touch the 0 line when delta T minimum will be maybe infinite. So, this is the decrease in area of the heat exchanger network. As the area will decrease, the fixed cost of heat exchanger network will also decrease proportional to the area, because we have seen that the cost law is A 1 plus B 1 area to the power C 1. Now, when delta T minimum increases from here to here, the hot utility cost and the cold utility cost are increasing linearly. This is a linear increase. However, the fixed cost is not linear, it is a non-linear in nature, because the cost law is A 1 plus B 1 a to the power C 1 plus the relationship of area and delta T minimum is also a non-linear relationship, and cost law is also a non-linear relationship. Whereas, here I am finding that the hot utility and cold utilities are increasing linearly. The cost of the heat exchanger varies with the heat exchanger area according to the relationship given below. Here we are using A plus B a to the power C, where A is the area of the heat exchanger network. The cost of the heat exchanger and coolers are given like this. So, these are the cost formula, and here this is 15,000 plus 50 area to the power 0.9, and for the heaters this is 15,000 plus 80 area to the power 0.9, and this is for the heat exchangers and coolers as well. Now, this shows you the variation of annual fixed cost of N with delta T minimum. Here we also see that this is a nonlinear relationship, and this was expected, because the area changes in a nonlinear fashion with delta T minimum, and that the relationship between area and the cost is also nonlinear. So, we expect that there will be a nonlinear relationship between the annual fixed cost and delta T minimum as well. Now, we take the cost of cooling utilities like this, that is 5 per kilowatt per year, cost of heating utility is 80 per kilowatt per year, and if we do so, then using the above values of the cost utility cost, the combined cost of utilities per year is computed for different specified values of delta T minimum and are plotted in the figure, which shows a linear relationship between annual utility cost and delta T minimum. This was expected, because the relationship between delta T minimum and the amount of utility was straight line, and we are already multiplying with it a factor. So, the relationship remains same. So, we are getting a straight line relationship between the cost of utility and the delta T minimum. Now, the total cost can be obtained by the summation of the annual operating cost and the annual capital cost, and this summation called TAC for specified values of delta T minimum as shown in the figure. Now, this is the fixed cost which is decreasing, and this is nonlinear in nature. This is operating cost, basically the cost of utilities, which is increasing in linear fashion. So, when delta T is increasing, this is increasing and this is decreasing. So, there are two opposite forces, one opposite to another, and hence a optima is expected in this case. When we join these two, that means this height plus this height we sum and put it here, this height plus this height we sum and put it here. Like this, we will, if we sum these two, this height plus this height we add, then put it here. So, if I do so, I get a curve like this, which is the summation of these two costs, and this passes through a minimum point which is here. So, I can say that this is my delta t minimum optimum, but this is somewhat flat, and this is invariably you get a flatter region where delta t minimum is optimum. So, if I convert this into the table, then for delta t minimum equal to 5, the capital cost is 148,362, the operating cost is 177,375, and the total cost is 325,737. When I change this to 10, it becomes the capital cost is 118419, but the operating cost is 200,750 and the TAC is 319169. And when I go for 15 degree, the capital cost decrease is less, that is 103354, and the operating increase is more, it is 224125, and the overhead is 327479. So, what we see that if I am near my temperature 10, then the TAC of the heat exchanger network will be lowest, and if I increase the delta T minimum more than 10, its cost TAC is increasing. As the operating cost is far more than the capital cost. So, obviously, the optimization, the delta T minimums moves towards the lower operating cost, and that is why you get a value 10 degree centigrade here. Super targeting is much less exact than energy targeting, because there are many uncertainties which creep into the computation, such as error in the estimation of heat transfer coefficients, total area of the heat exchanger network and its cost. We have seen that the computation of heat exchanger network cost depends upon so many things, and one of the important aspect is the heat transfer coefficient. Now, we have also seen that if the heat transfer coefficients are different of the order of magnitude in a heat exchanger network, then the minimum area which is computed using area targeting is not very accurate. So, obviously, these inaccuracies will creep into the super targeting also. The total cost curve, that is TAC curve, has a relatively flat optimum. This we have seen, it has got a flat optimum. So, there is a fair amount of flexibility. So, you have a flexibility, you do not need a razor sharp optimum delta T minimum. If it shifts a little bit, even then there will be very less loss, because the optimum area is flat, and that is why there is a flexibility in the selection of delta T minimum optimum. As long as the selected delta T minimum is not excessively small or large, a reasonable design can be obtained by using a good estimate for delta T minimum, at least for the initial stage. Thank you.